The diagram shows a circle C with centre O and a rod AB, the ends of which can slide around the circle C, so that AB remains a chord of C. The radius of the circle is R and the length of the rod is 2A. As the rod slides around the circle, the point B, which is a fixed distance of B from the centre of the rod, which I'll call X, traces out a circle with centre O again and radius small r. We need to show that the area between the two circles is pi a squared minus b squared. So where do we begin? Firstly, I'm going to try and take as much information from the text from above as possible. From the information above, we've established that px, so from P to the centre of the rod, is equal to B, and bx is equal to A. It's not explicitly said why bx is equal to A, but I can explain it quickly now. BA is 2A, and because BA is a chord of C, that means that any line from the centre, which is perpendicular to the chord and joins to the circumference, is a length bisector of BA. And that's why BX, the line from B to the centre of the rod, is equal to A. Next we have PO, which is equal to small r, because it's the radius of the smaller circle, and BO is equal to large r, the radius of the bigger circle. And for simplicity, and to help us later on, I've labelled XO as Y, a letter that has not been used yet. What we need to show is that the area between the two circles is pi a squared minus b squared. So we can define this area in terms of the r's. We know the area of the small circle is equal to pi small r squared, whilst the area of the large circle is pi big R squared. And so simply, the area between the two circles is pi r squared minus pi r squared, which we can factorise here, taking out a factor of pi, to get pi r squared minus small r squared. Judging by the formula given above, pi a squared minus b squared, you might be quick to say that large R is equal to A and small r is equal to B, but we cannot tell this for sure yet, and we have to prove it a different way. So we've established that the difference between the two circles is what's on the screen there, but now I'm going to take out that triangle in the centre between X, B and O and put on all the values onto the screen. We've established that Px is B, Po is R, Y is equal to XO and BO is equal to large R, whilst the whole length of BX is A. This is all the information I had on the previous screen. Using Pythagoras' theorem in a right angled triangle, y squared plus b squared is equal to small r squared, and y squared plus a squared is equal to large R squared. What can we do with this information, do you think? We can probably input the values for R squared and the large R squared back into the difference between the circles. And there we get pi R squared minus small r squared is equal to pi multiplied by y squared plus a squared, take away y squared plus b squared, the formula we just derived from the Pythagoras triangle. And so when we simplify this, we get pi multiplied by y squared plus a squared minus y squared minus b squared, and simply this is equal to pi a squared minus b squared. And there we have it. That's a simple proof to this question. So please leave a like and subscribe if you want to see more Cambridge Circle questions. But before then, I'll see you next time.